Hi, this is your lucky sir. Chemical kinetics we are discussing in that class 6. In this class, we'll go with zero order reactions. So, what is order? And what are the types of orders and all these we'll discuss in this session, right? So, the sum of the powers of the concentration terms of the reactants in the rate equation is known as order. That means, for example, rate is equal to K into A to the power X, B to the power Y. Then X plus Y is the order of the reaction. X is the order with respect to A, Y is the order with respect to B, and the sum is the overall order. The sum of the powers of the concentration terms of the reactants in the rate equation of the reaction is known as the order of the reaction. The rate equation is determined experimentally. Okay, now that means you cannot decide by seeing just the equation. Okay, now it is decided by the experimental values, and experimental values questions will be very, very interesting. And just show you one equation: A, B, and rate. Concentration 0.1, 0.1, 1 in 10 to the power of minus 2. Concentration 0.2, 0.1, 1 in 10 to the power of minus 2. Concentration 0.1, 0.2, 1 in 10 to the power of minus 2. What is the order of the reaction? These kind of questions will be there. So very interesting questions. You see, this is constant, it is doubled, no change in rate. Later it is constant, this is doubled, no change in rate. That means it is neither depending on A nor depending on B. So with respect to A 0, with respect to B 0. This kind of numericals will be very, very interesting. We'll discuss about such numericals also. So one line here, it is experimentally determined not by the equation. Hence, order of a reaction is an experimental quantity. So first we'll go with zero order reactions. Zero order reaction means when the rate of a reaction is independent of the concentration of the reactants. Rate is equal to K into A to the power 0. B also there, B to the power also 0. So it is not depending on the concentrations. Concentration of the reactant when you are taking with respect to that, it is 0. In such kind of cases, you can call this as zero order reaction. In zero order reaction, concentration of reactant decreases uniformly. Then we will take up these points. Rate of the reaction, rate is equal to K into concentration to the power 0. That means this term will become 1. So that is nothing but K. So rate units and K units will be same here. Hence rate of reaction has same units as the rate. That is moles per liter per second. This we were discussing in last class also. You can check again. For the zero order reaction, rate constant K is equal to R naught minus RT by T. Here square bracket when you are showing, this is nothing but the concentration. R naught means initial concentration. RT means concentration at T time. Okay, now T time means not T time, after T time. Okay. The time required for the completion of a zero order reaction is equal to R naught by K. This is the formula that you can take, where K is rate constant, R naught is initial concentration. The complete time required is R naught by K. Example for zero order reaction, the decomposition of gaseous ammonia on hot platinum surface. Ammonia decomposition on N2 and H2. That means if you change this temperature, then only the reaction will change. Only these conditions it is going to depend, not on the concentration of ammonia. For this you can write rate is equal to K into ammonia concentration to the power 0. It is 2 is here, but this is 0. That means this is the experimental value. At high pressure, the metal surface gets saturated with gas molecules. So a further change in reaction conditions is unable to alter the amount of ammonia on the surface of the platinum, and hence rate is independent of concentration of ammonia. Got it? So platinum surface, this platinum surface will be having some particular number of ammonia molecules. Okay, now even if you are changing the concentration, it can't increase the concentration of ammonia on its surface. So it depends only on the number of molecules present on the surface of the platinum. That's why it is going to be constant. Another example for zero order reaction is decomposition of HI on gold surface. 2HI, H2 plus I2, gold surface. Rate is equal to concentration of HI to the power 0. Like this you can write. And these expressions are very, very important. X is equals to KT. X is concentration at T time. K is rate constant, T is time. Or K is equal to X by T. Half-life period. Half-life period questions are very, very common for your JEE as well as NEET examinations. Zero order, first order, half-life reactions are very common. Half-life is equals to A by 2K. So here you can see T half is directly proportional to A. For zero order reactions, T half is directly proportional to initial concentration. A means initial concentration. Half-life period is directly proportional to initial concentration. This is the point of what I was saying here. Now you see the graphs. Concentration of reactant with time it is decreasing. It has to decrease, it decreases. T half and A it is directly proportional, so it is continuously increasing. Rate with time it doesn't change, so it is uniform. So these are the important lines, important graphs, important formulae for zero order reactions. Two examples I mentioned. One is decomposition of ammonia, second is decomposition of HI. For HI we are taking gold surface, for ammonia we are taking platinum surface. Done. Signing off. Lakshma Reddy sir.